It's fall in the Pacific Northwest, and rain has just moved through Seattle. In Longfellow Creek, a fisheries biologist wades into the shallows and finds something wrong. A coho salmon is spinning in slow circles at the surface, gasping, unable to hold itself steady against the current. Within minutes, it's dead. The biologist has seen this before, more times than anyone would like, and still doesn't have a name for what just happened in front of them. This fish had already done the impossible. It spent years in the open Pacific, dodging predators, growing strong enough to survive a journey most of its own siblings never completed. It found its way back, through miles of current, to the exact stream where its life began. It had one task left: reach the gravel beds upstream and spawn. It never got the chance. There are no wounds on its body, no signs of a struggle with a predator, no obvious disease, nothing a biologist can point to and say, "There, that's what killed it." And it isn't alone. Nearby, more coho are doing the same thing, circling, gasping, dying, sometimes within a single afternoon. These aren't old, weakened fish at the end of a hard migration. They're strong adults, arriving in good condition, close enough to their spawning grounds to almost taste success. And then, without warning, they die before they ever lay a single egg. For a species that has already survived years at sea just to reach this moment, that kind of death raises an uncomfortable question. If something this specific, this fast, and this consistent is killing fish that are otherwise healthy, something is reaching into these streams that nobody has been able to see or explain. Whatever it is, it keeps coming back, again and again, with rain. Coho salmon don't just belong to the rivers they return to. They belong to everything connected to those rivers. Orcas off the coast rely on salmon runs to survive. So do black bears, bald eagles, and a long list of other predators that time their year around the fish coming home. For the Yurok, the Puyallup, the Port Gamble Sklallam, and other tribal nations across the Pacific Northwest, coho are woven into diet, culture, and identity in ways that go back long before the streams had names on a map. This is a species that was already under pressure. A century and a half of dams, logging, and lost habitat had shrunk many coho populations well below their historical numbers. Every run that still makes it back is carrying more weight than it once did, biologically and culturally. So when biologists started tallying the die-offs in urban streams, the numbers were hard to look past. In some of the worst affected creeks, researchers found that up to 90% of the adult coho returning to spawn were dying before they could lay a single egg. Not 90% of a struggling run, 90% of the fish that had already made it home. Multiply that across an entire spawning season, and the math turns brutal. A run that should have produced thousands of new fish for the next generation can collapse into almost nothing, all in the space of a few rainy weeks. For a species with limited numbers left to spare, this wasn't a manageable loss. It was the kind of loss that, left unexplained and unaddressed, could erase a run entirely. Somewhere in these streams, something was killing salmon faster than they could recover, and no one yet knew what it was, or how to stop it. By the 1990s, Seattle had started trying to undo some of the damage. Culverts that had blocked fish from reaching upstream habitat were torn out. Native vegetation went back into stream banks that had been stripped bare by decades of development. Industrial pollution that once fouled these waterways was cleaned up, streamlined, regulated. It was the kind of patient, unglamorous work that rarely makes headlines, done by people who genuinely believed it would bring the fish back. For a while, it looked like it might work. Habitat access improved. Water quality improved. On paper, the streams were healthier than they'd been in generations. Then the die-offs started showing up, and they didn't behave like the leftover damage of an industrial past. They followed a pattern nobody had planned for. The deaths weren't concentrated in the most polluted waterways or the ones with the worst historical damage. They were happening specifically after it rained, and specifically in the streams that ran through developed urban land. Forested watersheds nearby, untouched by roads and pavement, weren't seeing the same thing. That distinction mattered. If decades of restoration work were paying off, biologists expected fewer fish to die, not more dying in a pattern tied so tightly to storms and city streets. Something about urban rainfall itself seemed to be the trigger, and that pointed toward a source no one had been actively investigating. It was a strange contradiction to sit with. The habitat had improved. The water looked cleaner by every standard test. And still, coho kept dying in a pattern too consistent to be a coincidence, and too specific to blame on old, familiar causes. Whatever was reaching these fish wasn't a leftover problem from the past. It was something new, something tied to the very streets and storm drains that ran alongside the restored streams, and nobody yet had a name for it. By the early 2000s, biologists studying these die-offs had enough data to know they were looking at a real, repeating pattern. They just didn't have an explanation for it. So they gave it a name instead: urban runoff mortality syndrome, a label for something they could measure but not yet understand. The pattern behind that name was consistent, almost mechanical in its timing. Rain would fall. Within hours, coho in nearby urban streams would begin showing the same signs: disorientation, loss of balance, gasping at the surface, followed by death. Streams running through forested land, untouched by roads, rarely showed the same losses. It wasn't randomly distributed, it was tied to the built environment itself. And it wasn't isolated to one creek, or even one city. The same syndrome kept turning up across multiple watersheds throughout the Pacific Northwest, in different states, in streams that had little in common except the presence of roads and rain running off them. In the worst-hit locations, it could kill nearly every adult coho that returned to spawn in a single season. A syndrome that consistent should have made the cause easier to find. Instead, it did the opposite. Every year, researchers went looking for a pathogen, a familiar toxin, some known culprit, and came back with nothing that fit. No pathogen showed up reliably in the dead fish. No known chemical matched the timing or the intensity of the deaths. For nearly 2 decades, urban runoff mortality syndrome was the closest thing scientists had to an answer, a description of a killer, not an identification of one. It told them where to look and when to expect it. It told them almost nothing about what it actually was, or how to stop it before the next storm rolled through. Faced with a mystery this consistent, researchers started where any investigator would, with the usual suspects. Urban streams have a long, well-documented history of killing fish, and biologists already knew most of the common culprits by heart. Low dissolved oxygen was an obvious candidate. Warm water stress from summer heat was another. Coho are sensitive to temperature, and cities tend to heat up the water flowing through them. Heavy metals and industrial toxins, left over from decades of urban runoff, seemed like plausible suspects too. And there was always the possibility of disease. A pathogen moving through crowded fish, weakened by a long migration, vulnerable in the final stretch before spawning. Each of these had killed salmon before, elsewhere, under different circumstances. None of them seemed like a stretch. If anything, they were the expected answer, the kind of cause biologists deal with regularly in urban waterways. It would have been an unremarkable finding. Bad news, but familiar bad news, the sort with known fixes and established playbooks. So researchers tested for all of it. They measured oxygen levels in the affected streams during die-off events. They tracked water temperature through the rainy season. They screened for the industrial toxins most commonly found in urban runoff. They examined dead and dying fish for the pathogens known to sweep through salmon populations. It was methodical, patient work, built on the reasonable assumption that the answer would be something they'd already seen before. Somewhere in that list of familiar causes, they expected to find the one responsible for wiping out entire runs of coho, season after season, storm after storm. One by one, the obvious suspects fell away. Oxygen levels in the affected streams came back normal, not the low, fish-suffocating readings researchers expected to find. Water temperature didn't spike in the way that would explain deaths this sudden or this severe. The known industrial toxins, the ones with a long history of harming urban fish, didn't match the timing of the die-offs closely enough to be the cause. And despite repeated attempts, no pathogen turned up consistently in the dying coho. No bacteria, no parasite, nothing that could account for fish collapsing within hours of a rainstorm. Every test came back the same way, inconclusive. The evidence kept ruling things out, and offered nothing to rule in. Edward Collage, an environmental engineer at the University of Washington, was among the researchers who spent years circling this problem. He later described it plainly as a serious mystery, the kind that resists the tools built for ordinary pollution cases. Standard toxicology panels are designed to catch known threats. This killer wasn't on any of them. That absence was its own kind of clue. If the usual causes had been responsible, the deaths should have shown up on at least one of these tests. Instead, coho kept dying in the same pattern, streams full of healthy-looking water by every conventional measure, fish dropping dead anyway within hours of rain. It meant the explanation biologists had been reaching for, the familiar, expected one, wasn't the answer. Something else was moving through these streams, something invisible to the tests built to catch it, arriving with the rain and disappearing before anyone could trace where it had come from. Whatever it was going to take a different kind of investigation to find. If the usual suspects were innocent, researchers needed a new starting point, and they already had one clue that had held up through every test. It always came back to rain. Whatever was killing these fish wasn't already sitting in the stream. It was arriving with stormwater, washing off the streets and parking lots that fed directly into these urban creeks. That narrowed the search, but only slightly. Road runoff isn't a single substance. It's a moving mixture of thousands of different compounds, residue from vehicle exhaust, brake dust, oil, pavement sealants, and whatever else accumulates on a road surface between one rainstorm and the next. Somewhere inside that chemical soup was a killer potent enough to drop a healthy adult coho within hours. Finding it meant sorting through nearly all of it. Collogier's team at the University of Washington took on the search, and it wasn't fast work. They collected runoff samples directly from affected streams and began breaking them down into smaller and smaller chemical fractions, testing each piece against live coho in lab tanks. Which fraction killed fish? Which didn't? Then narrowing again and again, discarding compounds that had no effect, isolating the ones that did. It was slow, exacting, and largely invisible work. The kind of research that doesn't produce headlines for years at a time because the answer keeps refusing to show itself. Community scientists helped track die-offs in real time. Biologists supplied fish and field data. Environmental chemists ran the lab work, sample after sample, season after season, chasing a compound they couldn't yet name. 2 decades is a long time to search for something you can't see. In a mixture with thousands of possible culprits, using a method that only tells you what something isn't until it finally tells you what it is. But by narrowing the runoff down fraction by fraction, the team was closing in on something real, a specific, identifiable source, buried inside all that road residue, that nobody outside a chemistry lab had ever thought to suspect. In 2020, after years of elimination, they finally found it. And the answer didn't come from a factory, a pipeline, or an industrial site. It came from something sitting on every car in America. The compound Collogier's team finally isolated was 6-ppd-quinone. And to understand where it came from, you have to go back to a chemical that has almost nothing to do with fish at all. Since the 1950s, tire manufacturers have added a compound called 6-ppd to nearly every tire produced. Its job is simple: protect rubber from ozone, the reactive gas in the atmosphere that would otherwise cause tires to crack and degrade over time. It's an antioxidant, essentially, built to make tires last longer on the road. For 70 years, it worked exactly as intended, and nobody thought twice about it. But tires wear down. Every mile driven sheds microscopic particles of rubber onto the road surface, a slow, constant residue left behind by ordinary traffic. Those particles sit on pavement until rain washes them into storm drains, and from there, into nearby creeks. Along the way, the 6-ppd inside those particles reacts with ozone in the environment and transforms into something new, 6-ppd-quinone. That transformation is where the story turns. 6-ppd-quinone is toxic to coho salmon at concentrations low enough to be difficult to detect without targeted testing, and lethal enough to kill an adult fish within a matter of hours. It doesn't appear to attack a single organ the way a familiar toxin might. Instead, exposed fish lose coordination and orientation almost immediately, the same disorientation biologists had been documenting for 2 decades, and death follows quickly after. For 20 years, researchers had been testing for pollutants with a track record, established toxins with known effects, chemicals already on the watch list. 6-ppd-quinone wasn't on it. It wasn't hiding because it was rare or exotic. It was hiding because it was everywhere. A byproduct of an antioxidant so ordinary, so embedded in daily life, that no one had thought to test for its transformation product in a salmon stream. Collogier and his colleagues published their findings in the journal Science. closing a case that had opened with a handful of dead coho in a Seattle creek and ended with the identification of a chemical born from something as unremarkable as everyday traffic. The killer wasn't an industrial accident. It wasn't a rare contaminant with a single traceable source. It was the ordinary aftermath of driving, dissolved invisibly into rainwater, moving from asphalt to storm drain to stream, with every storm that passed through a city. 70 years of tires, 70 years of rain, and nobody had made the connection. Until now. Identifying 6-ppd quinone answered a 2-decade-old mystery. It didn't come close to solving the problem behind it. Tires aren't a contained pollution source, the kind you can regulate at a single factory or clean up at a single site. They're on every vehicle, on every road, in every city and suburb where salmon streams happen to cross paths with pavement. Wherever roads and rain-fed creeks intersect, the conditions for another die-off already exist. That reality pushed the fight from the lab into the political arena. The Yurok, Puyallup, and Port Gamble S'Klallam tribes petitioned the Environmental Protection Agency, asking the agency to regulate 6-ppd as a toxic substance under the Toxic Substances Control Act. For these tribal nations, the stakes went beyond ecology. Salmon runs decimated by a chemical nobody had chosen to expose them to threatened food systems and cultural practices built around these fish for generations. But regulating 6-ppd isn't as simple as banning a single product. Virtually every tire manufactured today contains it, because without some form of ozone protection, tires degrade and fail faster. A real safety trade-off, not just an industrial convenience. There is currently no safer alternative in wide, mass-market use to replace it. Solving this problem doesn't mean shutting down one polluter. It means asking a global industry to redesign a product used by nearly every vehicle on the planet, without introducing new risks in the process. That gap between identifying a cause and eliminating it is where this story sits now. Scientists know what's killing these fish. Regulators have been asked to act. But the compound is still washing off roads with every storm, into the same creeks where researchers first noticed something was wrong, and there is no quick fix waiting on the other side of that knowledge. Solving one mystery, it turned out, was only the beginning of a much larger, much slower fight, and even that fight was about to run into problems that had nothing to do with tires at all. While Kologi's team was tracing 6-ppd quinone through Seattle's storm drains, entirely different threats were closing in on salmon elsewhere. Threats with no connection to tires, no connection to cities, and no single culprit to isolate. In California's Central Valley, researchers studying the Sacramento River identified a thiamine deficiency, a shortage of vitamin B1, that likely killed roughly half of the newly hatched winter-run Chinook fry in back-to-back years. The cause traced back to the ocean itself. Large-scale shifts in the marine food web had changed what adult salmon were eating before they returned to spawn, and that dietary shift left their offspring without enough of a nutrient essential for basic development. A problem born hundreds of miles offshore was showing up as dead fry in a California river. Farther north, along the Klamath River, a parasite called Ceratonova shasta has been surging. During a recent outmigration season, researchers sampling salmon found that nearly half of the fish they collected tested positive for it. Unlike the tire chemical, this threat isn't new to salmon rivers. But warming water conditions appear to be giving it room to spread further and hit harder than it has in the past. And across California's engineered river systems, a separate study found that decades of channeling rivers into fast, simplified waterways has created what researchers call an ecological trap. Historic wetlands that once buffered young salmon against extreme weather have been replaced by narrow, controlled channels. Now, both severe droughts and violent flood events are proving lethal to juvenile Chinook in ways the historical, unaltered rivers never were. None of these threats share a cause. One begins in the ocean. One is a parasite responding to warmer water. One is the long-term consequence of how rivers themselves have been rebuilt. They're unfolding in different states, on different timelines, against different runs and different life stages of the same species. But they are unfolding at the same time, and for salmon already stretched thin by a century and a half of habitat loss, that overlap matters more than any single threat on its own. Solving the tire mystery didn't remove the other dangers waiting in these rivers. It only revealed how many separate battles this species is now fighting at once. Go back to that first image. A coho salmon spinning in slow circles in Longfellow Creek, gasping, dead within minutes. with no visible wound and no obvious cause. For 20 years, that scene repeated itself after nearly every rainstorm, and nobody could explain why. The answer, when it finally came, wasn't dramatic. There was no oil spill, no factory discharge, no exotic disease sweeping through the population. The killer was rubber dust, worn off ordinary tires during ordinary commutes, dissolving invisibly into rainwater, and drifting into a stream that fish had been returning to for generations. That's the deeper truth sitting underneath this story. The threat to salmon was never a single, dramatic villain waiting to be caught. It's the accumulated weight of modern life pressing on these rivers from every direction at once, tires shedding chemicals with every storm, rivers reshaped into channels that no longer buffer extreme weather, oceans shifting in ways that starve young fish of what they need to survive, parasites spreading further as water warms. Each of these, on its own, might be survivable. Together, they add up to something far harder to outlast. The mystery in Longfellow Creek is solved. Researchers know what it was, they know how it moves through these streams, and they know, roughly, what it would take to stop it. But knowing the cause and removing it from a world built around cars, roads, and rivers, already re-engineered for something other than fish, are two very different problems. The salmon that make it home now are swimming through more than a migration. They're swimming through the accumulated residue of everything built along the way. And for this species, the mystery may be solved, but the crisis it uncovered is only getting started.